Homework 4.3, page 391. Now, problem 119 is a straightforward one of separation in the sense that there's nothing to separate. There's only y on the other side. That's called an autonomous equation. So you put the y on the bottom and then put the dt on the other side, integrate, and then you end up with some kind of plus or minus situation, which we will just, well, ignore, okay? I mean, c can be plus or minus, yeah. And then you plug in t, when t equal to 0, y equal to 0. So the plus or minus c has to be 1. And plug it in, then that's your answer. Now, the next problem, 121, is very similar with the only difference is that y has to be equal to minus 1. So you do almost identical thing and then end up with a similar answer. Yeah, except similar but quite different because the top one, e is to the positive t, whereas the bottom one, there's a negative sign on top of e of t, which makes it a very, very different answer for something that's just slightly different. Okay, next let's look at problem 125, which again is fairly straightforward. Where you have the problem is easily separable, so you put the x on one side, y on the other side, do the integration, and then that's about it. And then you do have to pull y out of there, which in this case is fairly easy. So that's that. And then 131, similar situation. We have a standard integral of 1 over the square root, which by rule 15 is a sine inverse of y. And then you plug y out by slapping sine on both sides, and that's your answer. Next, problem 133, we have, again, fairly similar situation, right? We have dy by dx is e to the power y over e to the power x. So you put the y's on one side, x to one side, at the other side, and then integrate, and then you come up with some kind of an answer. But you do have to plug in the initial conditions to figure out what c is. Well, c conveniently turned out to be 0. So here's the answer that the book gave you. Let's see. Okay, y equals to minus natural log, etc. Now that is actually just y equal to x. I mean, that's, yeah, because the natural log and e reverse actions. And then the negative sign in front cancels out the negative sign on top. So, yeah. So it's just x, okay? Next, let's look at problem 139. We are going to integrate. Again, the integration is quite straightforward. If you break things, split things in two parts, the t's and the x's, then you integrate. It becomes, well, apply rule 15, okay, which means the integral of the square root is sine inverse, and 1 over square root, that is. And then the integral of the natural log is rule 46, which is all that stuff. And then you slap sine on both sides, and that's your answer. However, you're also supposed to calculate what is the value when t is 0, right? When t is 0, x is 0, and with that, you're going to plug it in, do some algebra, and figure out what c is. And c end up being 0. So then the final function becomes this thing down here, which turns out to be correct. All right, I think the answer in the book, for some reasons, have a negative sign in front. We don't know why, but we can change it because sine of negative theta right here is just negative sine theta, so it's not a big deal. And then, okay, next let's do 151, because I did that first before 145, so let's look at that. And 151 is an almost identical problem to the example in the book about the salt tank. Well, you have liquid going in. The liquid is going in at where's the liquid? Yeah, the liquid is going in at 2 liters per minute, and the concentration is 0.1 kilogram per liter. So you multiply it together, that's how much salt is going in, the rate of salt going in. Similarly, the salt is going out at the tank over 100, that's the concentration, because you don't know how much salt is in there. So, so U is the amount of salt, so you divide it by the 100 to be the concentration times 2 liters per minute, and that together becomes how much salt is going out. So then you get a very simple differential equation, which you integrate and the answer quickly come out. Or you can just copy the answer. The integration is already done in the book example, right? So you can just copy that down, plug in a few different numbers, and come up with the right answer. All right, so, but I did do the work again on the bottom. Let's see if you can see it. So if you need to look at the details, you can see that. See, the book answer is correct. Now next, let's look at problem 145, where yeah, again, you're doing some simple integration. Okay, these are all, these might give you the impression that differential equations is easy. Well, these certainly are. You just you separate the variables, the y on one side, x on one side, integrate, then pull y out of there. Okay, you end up with y squared, so you got to take the square root, and it's 1 over y, so you got to push the other side onto the push the other side down the division line, and then you get the right answer. That's 145. All right. Now problem 157, I'm pretty sure the answer in the back is wrong, but however, I could be wrong there. I've looked over my stuff and can't find any mistakes. So I will just present it to you. And if my answer turned out to be wrong, just go with the book's answer if you find something wrong with my answer that I missed. So, and the problem, of course, is very simple. It's identical to the pizza problem. This is the ice cream problem, and they're both cooling. They're just cooling to a different point. Now, so let's look at problem 157, where we follow the formula, and I just follow the formula in the book. I didn't bother even doing the integration, okay, because it's the exact same integration. So the formula is this. And then after you follow the book example, the example 4.13, and then you do a bunch of algebra, and I hope I didn't make a mistake in here, and that better not be why my answer is different. But anyway, I looked over it several times. I can't see anything wrong with what I wrote. So so anyway, I did the algebra, and then eventually came up with some kind of answer, which is 24 hours. Yeah, and I can't seem to find what's wrong with what I wrote. So I plotted the problem on the calculator, and it looks pretty good. My answer all seemed to make sense. It started at time 0, it's at 210 degrees. See on top that dot there. And then at time 2, it becomes 170, and then eventually it went down to 30 only at time 24.91. So that's the answer I got. Yeah, so see if you can figure out where I'm wrong and the book's right. Otherwise, I'm right and the book's wrong. But either way, let's move on. So problem 167 says that leaves accumulating at a rate of 4 grams per year, and then they decompose at a rate of 10%. So what we're going to do is, like the book, we'll set, this is the same as the tank problem, okay, except now we're doing rotting leaves. So let's consider leaves. Let U of T represent the total thickness of leaves, right? And then, so then the change is that the leaves increase by 4 grams per year, right here. Is it 4 grams? Yeah, it's 4 grams per something. What did it say? Let me check. Okay, it's actually 4 grams per centimeter per year. And then fine, which is fine. So it gains 4 grams per year, roughly speaking. And it goes out at, we don't know how much it goes out, but we know it goes out at 10% of, it decreases by 10% of the total amount of leaves. So it's 4 minus 0.1 U, and that's the rate of leaf change, okay? And then so you integrate that simple solution, simple equation, and then come up with some kind of an answer that has decimal points in it, which is fine. And then you let, when T is 0, we let U equal to be 0. The book, the question doesn't say how thick was it to start with, so we'll assume that the scientists swept the floor and there's nothing. So then if we assume that, then we come up with the equation, a value for c, and which is that equation. And as t goes to infinity, then u approaches 40 grams per centimeter. So eventually that will be sort of the equilibrium rate. And all right, and that is the right answer. So so that's the end of this section.